So this is chapter 3, section 7 of calculus. So what we're trying to do is, these are all about optimization problems. So we're trying to find the maximum or minimum of something. And so you think back to what we've done in previous sections here, because all of this in chapter 3 is about applying the derivative. So think about how with graphs, how do you find the max or min? Well, we're going to do the same thing here. And so we're going to be setting the derivative equal to 0. We're going to find an equation for what we're talking about, what we want to maximize or minimize. And then when we take the derivative of that equation and set it equal to 0, that'll be where it turns around. So that'll be where it's a minimum or a maximum. So let's see this. We can look at it on Desmos too to figure out how that works. So here's the problem. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in the picture. Ooh, maybe we should go get that picture. What dimensions will produce a box with a maximum volume? So we can just draw the picture. So we draw a box. I draw another box. And there's our box. Beautiful. Beautiful. And beautiful. So remember, the box has an open top. It's like a fish tank. So let's write equations for what we know. We know that the surface area is 108 square inches. So the base of the box is square. I didn't see that. Let's go to the textbook and let's grab that. No, good. We're right there. There we go. That is going to be helpful for us that the base of the box is square. Sometimes that crashes my iPad, sometimes it doesn't. And this time it's going to. Man, why does it do that? Is it too big? It's going to do it again. Yeah. Man. All right, we're back. And we got the picture. So here's our box. It's got a square base. And you can see decently in their drawing that it's got no top. So we need to start write our equations. So first off, let's write the equation for the surface area. So I'll write SA for surface area. And you don't think about a formula for the surface area of a box. You just kind of look at it. So you've got each side. So you've got this side here. That's X times H. Notice you have the same thing back here. So 2 of them. You've got this side right here, which the picture doesn't make that very obvious, but that's also X times H. And then you've also got that on the back side. So we actually don't even have 2 X times H's. We have 4 X times H's. And then we've got the bottom, which is X times X. And we don't have 2 of those because the top is open. Okay, so that's our equation for the surface area. And what is the surface area? The surface area is 108. They actually tell us that. So I didn't even need to put SA there. 108 equals that. Awesome. That's going to be useful. So now, what is it that we're actually talking about here? The volume. We want to maximize the volume. So let's write an equation for the volume. What's the volume of this thing? Well, it's X, base times width times height, or length times width times height. So X times H. So the volume is X squared times H. I don't know why I did a dot there. X squared H. So now here's the thing. Like we said, we want to take the derivative and set the derivative equal to 0. And that'll be it. But it's not good to have 2 different variables there when we take the derivative, because then we'll have to do like implicit differentiation type of stuff. So that's what the top equation is for. We've got to eliminate one of those variables. So I would just eliminate the H. Well, for one, notice it's going to be a lot harder to get x by itself since it's in these two different places and it's squared. You'd have to use the quadratic formula, actually. So definitely let's solve for h up here. So let's take this top equation and solve it for h. So subtract x squared and divide by 4x. That's going to be a tough equation. I guess not. So that is h. H equals that. So now we come down here into the volume equation and replace this h with it. So now we have an equation for the volume that only involves one variable. And so now we should take the derivative of it. So that's the key thing with these, is when you take the derivative, generally you only want to have one variable there. And now before you take the derivative, we definitely should simplify this. And I'm even going to distribute the x. So I have 18x minus x cubed, all of that over 4. So that'll be much easier to take the derivative of here. Because now we can just use power rule. So we'll get dv dx equals 18 minus 3x squared, all of that over 4. You can do that, right? Because 4 is just a constant. It's just like you're multiplying by 1/4. And so now what do we want to do? We want to set this equal to 0. Because that'll show, if we put this in the graph, like we could graph this equation, you can even see it's going to be like an upside down parabola, negative x squared. And this is going to be like, for each point here, like if that was just going to make up numbers, that's saying like if the x value is 2, it's going to have a volume of 5. And so on. And so what we really want to find here is this point at the top where it's going to have the maximum, where that's going to end up being the maximum volume, since this equation represents the volume. The function represents the volume. So that's what we're going to do. We're going to set that equal to 0. So we're going to multiply by everything by 4. I'm going to go ahead and divide everything by 3. And then add the x squared to the other side. So I get x squared equals 6. And then I'm going to square root both sides. I'm not confident in that, though. Let's slow it down. So I multiply both sides by 4. 18 minus 3x squared equals 0. I add the 3x squared and divide by 3. Okay, so that was correct. So x is, so of course, plus or minus the square root of 6. But we're talking about side lengths, so we don't actually want the minus. Just the positive square root of 6. And there we go. That's pretty much what we want, right? I guess I was a little wrong saying, because we're not looking at this parabola type of thing. We're more looking at this x cubed type of equation. And you can kind of get an idea of what that looks like. It's going to be something like this. So this is that negative root 6 that we just found. But in reality, that's just doesn't make any sense because you can't have negative side lengths. That's the positive root 6 that we just found. So that's what x has to be to maximize the area, is the square root of 6. What do they actually ask for? Yeah, what dimensions will produce a box? So we know we want that to be the square root of 6, and we know we want that to be the square root of 6. So now we should come back into our h equation that we just found here, and we can use that to solve for what h should be. Because now we know that x is the square root of 6. So 18 minus the square root of 6 squared over 4 times the square root of 6. So let's see, let's simplify. So the square root of 6 squared is 6. So 18 minus 6 is 12. 12 over 4 root 6. So I can definitely do that and call this 3 over root 6. And then maybe I want to rationalize. So multiply by root 6 over root 6. So it ends up being 3 root 6 over 6. Or root 6 over 2. So our height needs to be the square root of 6 over 2. And I was worried about that at first when I was solving that answer, because normally you'd expect things to all be equal. But the whole reason that's not true is because the top is missing. So that answer makes sense to me. You have square root of 6 by square root of 6 by square root of 6 over 2. And what we can do is, it's not the best visualization, but let's look at our equation for the volume. 18x x minus x cubed divided by 4. And that's our answer right there. Square root of 6. Square root of 6 is 2.45-ish. Or 2.449. Yeah. So that's the value of x that'll maximize our volume. The biggest box we can build, if we know that surface area has to be 108, is root 6 by root 6 by root 6 over 2. Cool. So that's the idea with all of these. We've got to write some equation for what we're trying to minimize or maximize, and then take the derivative of it and set it equal to 0. We're going to do the same thing here. Which points on the graph of f minus x squared are closest to the point 0, 2? Okay. Well, I'm going to graph this just so we can get a good visual of it and get a good prediction. So 4 minus x squared. So that's the minus x squared graph, but shifted up 4. So I might as well be specific with the points. Let me do one more. 5. 1, 2, 3, 4, 5 over 1. And here. All right, so then I'm going to draw the parabola. So that's our graph that we're working with. And we want to know what points on the graph are closest to 0, 2. And I don't know, we can look. I mean, we actually should know the answer is where it's perpendicular to the tangent line, right? Where the tangent line and the line to the thing is perpendicular. That's intuitively where it should be, right? But we can do some calculations to see if that's actually true. Maybe we'll do that both ways. So definitely the way to do this problem, like we did the last one, is to write the equation. So we should envision this as 2 points. The point 0, 2 and the point x, 4 minus x squared. Right? That's just all the points on that parabola. And now we can write an equation for the distance. Is that what we should do? Do the square root of, because it'll already only involve x. So x minus 0 squared plus 4 minus x squared minus 2 squared. That's what the distance equals. So the distance is the square root of x squared. Oh, right, you have to square that. Okay. So this is 2 minus x squared, and then we're going to square it. So it's going to be plus 4 minus 4x squared plus x to the 4th. Go ahead and combine some like terms. X to the 4th minus 3x squared plus 4. You can almost factor that, but you can't. I don't know if that would help anyway. But that's what our distance is. Now we can square root it. And yeah, we can square root it. We can take the derivative and then set it equal to 0. So we take the derivative. The derivative of the square root is 1 over 2 root times the derivative of the inside times 4x cubed minus 6x. Yeah. Okay, that's very nice. That's actually very, very nice, because now we want to set that equal to 0. So we're going to multiply both sides by the bottom. I could cancel out the 2, but I don't really need to. Yeah, I'll factor out the 2. And that's left with 2x squared minus 6 equals 0. So we get either x equals 0, which doesn't make sense. Or does that not make sense? I don't know. We'll say x equals 0. And we factored out the 2, so that's supposed to be 3. 2x squared minus 3 equals 0. So here we get x equals plus or minus root 3 over 2. But why do we also get that x equals 0? Oh, is that a maximum? Because that's a maximum distance. So now what I would do, if I wasn't looking at the graph, is I would come back up here to our distance equation and plug in those values. So I'd say at x equals 0, the distance is 4. At x equals root 3 over 2, oh my goodness, you're going to have root 3 over 2 to the 4th. Let me change colors here. Root 3 over 2 to the 4th, which is root 3 squared squared, so 3 squared, so 9 over 16, minus 3/4 times 3, minus 9/4, plus 4. So 9/16 minus 9/4 is 9/16 minus 2 9/16. So that's minus 9/16 plus 4, which is 4 times 16 is 64, minus 9, 55. 55 over 16, the square root of 55 over 4. Is that less than 4? What's the square root of 55? Let's see, there's 36, there's 49, so it's between 7 and 8. So if you'd say it's like 8 divided by 4, it's like 2. So that is less than that. So that means that's like the maximum. So you're still going to get, that's like a maximum distance in this region. See how like as you get closer, I guess I could do this. And you could say like as you get closer to here, the line gets shorter. That roughly there is the minimum. But then it gets longer again, longer again, longer again, longer again, longer again. And then here, this is like a maximum distance, a relative maximum distance. Because then it gets shorter and shorter and shorter and shorter and shorter. Somewhere around here, it's the minimum distance again. And then it gets longer and longer and longer. So this just gets longer forever. So that's why you don't see that. Like we're not finding that this is the absolute maximum distance. That's a relative maximum distance at the vertex. That's why we got x equals 0. But that means the minimums have to be these two values. What was it? Plus or minus root 3 over 2. And that's going to be a little more than 1? No, that's going to be a little less than 1, isn't it? Root 3 over 2? Let's look at this on Desmos. So we've got 4 minus x squared. I guess we could find the point too. So what happens when we plug in root 3 over 2 into this? You get 4 minus 3/4, which is 13/4. So can I graph the point root 3 over 2, I guess like that, root 3 over 4, comma, 13/4. Well, that worked out. And then let's graph the point that we cared about, 0, comma 2. That's not right. Holy moly, that's not right. Where did we mess up here? I mean, look at that. That can't be a minimum distance. Is our distance equation wrong? 4x cubed minus 6x. No, 4x cubed minus 6x was pretty good for the top. And then, yeah, I factored out the x. Factored out 2x. So that's why it's 2x squared minus 3. Oh, it is the square root of the whole thing. This is 2 here. Oh, that's... It is the square root of 3 halves. It's the square root of 3 halves, which means this is 5 halves. 10/4. That looks proper. Okay. Ooh. It was the very last step. It's the square root of the whole thing. So that means all of that is wrong too. But that still all makes sense. Ugh. That was bad. But there we go. So that's the answer. That's the point that is the closest. Root 3 halves, comma, 5 halves. Nice. Okay. So I just simply messed up the very end. That's embarrassing. Now I want to try to do this a different way. See if that's even possible. I want to use kind of the geometry idea that the closest path is when the slope is perpendicular. And then we want to find where they intersect. Huh. Is that how I'd want to do that? I would want to write an equation for the tangent line, add an x value. So how am I going to write an equation line at the x value? Well, I need a point and I need a slope. So I know the point is still just this point right here. And I know the slope is negative 2x if I just take the derivative. So I can go negative 2x, that's the slope, times x minus x. Okay, maybe that won't work out. Oh, right, no, but that's just the x. This is x minus, like, a. So that should be like an a. And we want to solve for the a. And then this is y minus, putting a in for x, 4 minus a squared. Or maybe I need to write the equation of the line between that point now. So let me say that's definitely... Well, that's actually just slope-intercept form. So it's the slope plus 2 equals y. That's the equation of that line. And I know that slope needs to be perpendicular to the point where they cross. Well, I already established that a. So the slope is negative 2a. So I know this slope needs to be 1 over 2a. Can I solve this equation for a? Or the x is still going to be in there, though. I'm not sure what the x and the y are in this scenario. I'd get the y out, but the x would still be in there. Maybe I'm not sure how to do it this way. So I'm trying to write the equation of this line. And then write the equation of this line. Like, and then solve for where they intersect, but we know where they intersect. Well, we don't know where they intersect. We want to solve for that a value where they intersect, which is the point that it's going through. But I somehow have to be able to get all of the x's and y's out of there. I don't see how that's going to work out. So I can get like the positive 2ax. I could get a positive 2ax by itself, but that's a lot for one. But that could do some good simplifying. Let's look at this thing and try to simplify it. Negative 2ax plus 2a squared equals y minus 4 plus a squared. So see, I can at least like get an a squared by itself and say that a squared... Oh, no, I can't though, because there's still an ax. But I could go a squared minus 2ax is y minus 4. So that would be my like a squared minus y plus 4 equals 2ax. And so that's how I'd like put that in there. But then I just have an equation involving a and y. And the y is not going to just go away, right? I'm going to have 1 over a squared minus y plus 4 equals 2ax. So then I'd end up, equals 2ax. What? No, equals y. Also, there's the plus 2 there. Geez, that looks like it's on the bottom, but there's the plus 2 there. Equals y. And that really messes it up. Holy moly, that really messes it up. Alright, maybe I'll just not think about that. Let's go to the next one. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and the right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? I'm definitely going to have to come back to that last problem. I'm not going to feel okay just leaving that there. But for now, we got a rectangular page that's going to have 24 square inches of print. The margins at the top are 1.5. The margins on the left and right are 1. What should the dimensions of the page be so that the least amount of paper is used? Whoa, that's kind of strange. So we've got our thing. We know we have margins. We know that this distance here, the top and bottom, is 1.5. We know the left and right are 1. Okay. And what we want is the dimensions of the page so that the least amount of paper is used. We want to minimize the dimensions of the piece of paper. So let's go, that whole thing is x, that whole thing is y. So the area that we're trying to minimize is x times y. But we've got to write the other equation so that we can make that with only one variable. That was nice about what we did on the last problem, is it already had one variable, but here we got to make it to have one variable. So let's write the equation for the inside area. So that's 24. We got to write it in terms of x and y. So think about, what is this distance? Well, it's x minus those margins. This is y minus those margins. Well, that won't be bad. So we know that x minus 2 times y minus 3 has to equal 24. And then we've got to solve that for one of those variables, x or y. Okay. Okay. Well, I'll solve it for x, I suppose. And honestly, the best way to do this is divide everything by y minus 3. Because y can already not be 3. So you divide everything by y minus 3 and then add 2. So x is 24 over y minus 3 plus 2. And so I'll just go for that. That's what x is. So when we do this substitution here, it's going to be a equals 24 over y minus 3 plus 2 times y. And then before I take the derivative, I am going to simplify this a bit. So I'm going to combine this stuff in the middle. 24 plus 2y minus 6 over y minus 3. But then I've also got to distribute this y on the top. So then I'm going to have 2y squared, 24 minus 6 is 18, minus 18y over y minus 3. And it looks like you can cancel stuff out, but no. So that's the equation for our area. So now we've got to take the derivative of that. So dA over dt, or dx, or dy actually, is quotient rule. So the derivative of the top, 4y minus 18 times y minus 3 minus the original of the top, 2y squared minus 18y times the derivative of the bottom, which is nothing. All of that over y minus 3 squared. Holy moly. And now we want to set that equal to 0. Well, at least we've only got a quadratic. We're really working into the next problem. But we set it equal to 0. We just have to look at the top, I suppose. So I need to distribute everything on the top. So 4y squared minus 12y minus 18y plus 18 times 3, which is 54, minus 2y squared plus 18y. Okay, so that's nice that that goes out. Oh, no, because you still have the minus 12y. But that does go out. So we have 2y squared minus 12y plus 54 equals 0, and we can divide everything by 2, so y squared minus 6y plus 27 equals 0. That's an imaginary answer. How do I end up screwing all these over so much? I felt like I went slow enough to make sure I got it right. 24 inches of print, 1.5. So we set up our dimensions. X minus 2 times y minus 3 divided by y minus 3. And add 2. So 24 over y minus 3 plus 2 is equal to x. So then I replace that with x. 24 over y minus 3 plus 2 times y. And I combined the fractions in the middle. So that's 2y minus 6. But then I had to distribute the y that was on the outside. So that's why it was 2y squared, and that was minus 18, so that was minus 18y. So I had 2y squared minus 18y over y minus 3. Okay. So then I took the derivative. So it was 4y minus 18 times y minus 3 minus 2y squared minus 18y times the derivative of y minus 3 over y minus 3 squared. But it does seem like it's the negative 18 times the negative 3 where it's going weird, because that's getting me the plus 54, which is huge. And I see that it's imaginary because the b squared minus 4ac. b squared minus 4ac is going to be negative. This is not the best. I know that my process has to be right. It's x minus 2, and it's y minus 3. So I divided by y minus 3 and added 2. Let's look at our area equation on Desmos. So what was our area equation? X and y are decently interchangeable. So I'll say 2x squared minus 18x divided by x minus 3. Okay, that can't be right. Because, yeah, that doesn't have a maximum or a minimum. Or, I mean, actually, would it if... No, that didn't work out. But no, now I think that can't be right because that doesn't have a maximum or a minimum. Which makes sense what we found based on our derivative, but then that means we did this wrong somehow? Holy moly, this is plus 18y. How did I make that mistake? And look over it so many times. It's 24 minus 6. That's plus 18y. Oh my gosh. Alright, let's see if I can go through and fix everything then without having to redo it all. So that's a plus 18, and that's a plus 18. That's it. That's all that's going to go differently. But that is going to fix things for sure, because that's going to be a minus 54, which already fixes the imaginary answers issue. And what else? This is going to be a positive 18y. So that's the two fixes up there, and then I have the other fix over here. So that should just be minus. So those are still canceling out. That literally the only thing that changes is that this is going to be a minus. But that's all I needed to change. So I could confirm by graphing my new equation here. 2x squared plus 18x divided by x minus 3. So yes, now we will have maximums or minimums. So we want minimums, and see this minimum's not going to count because it's negative. We can't have the negative values. So the other one is what we're actually looking for. So let's see. Now we can just factor this, which is awesome. We can just factor it and find the answers right away. It's y minus 9, y plus 3. So we get the negative 3 and the positive 9. And you see, that's what we just saw. We saw the negative value. So now if we highlight that other point, there's our positive 9. And that shows us that we're going to use the area of 54. We're going to use a paper area of 54. But what did they really want? They wanted what dimensions? So we just found that y, now x and y does matter because the margins are different. So we just found that the y should be 9. And then what are we going to use to find the x? We're just going to use this formula right here. So we plug in 9 for y. 24 divided by 6 is 4 plus 2. So x should be 6. And we can see that in our Desmos graph, how they said that the area was 54. It said the area was 54. So that means it has to be 9 times 6. Beautiful. And so see, this graph is representing all the different areas we could use. The negative one doesn't count, of course, because you can't have negative side lengths, but these are all the real ones. And so you see that right there is how you're going to minimize it. All right, I'm going to pause for a second. All right, so let's go back to this problem and let's do it the other way. So we already knew the answer was the square root of 3/2 by doing it the calculus way. But we can do this without calculus. Well, actually, no, because we need to know the slope of the tangent line. So we can do it with easier derivatives. So that's the derivative of 4 minus x squared is negative 2x. So we know the slope, if we think about this point, a comma 4 minus a squared, where they intersect. We don't know where it is, but we know it must exist, so that's what we're looking for. Well, there's a lot of points where they intersect. So we know if where they intersect, that's the slope, negative 2a. Now we want them to intersect where it's perpendicular. So we want the equation of the other line to be perpendicular to that line. So what do we want the slope to be? Well, if the slope of the tangent line is negative 2a, we want the slope of the perpendicular line to be the opposite reciprocal, 1 over positive 2a. So that's the slope of this purple line we have drawn here. So let's write the equation of that line. So that's the slope, and it's a nice y-intercept. So we can just treat it as slope-intercept form. 1 over 2a, the slope, times x, plus 2, the y-intercept, equals y. That's the equation of that purple line that's perpendicular to the parabola. And now we can say, well, this point that it's going to go through, this is like our x comma y right here. We know that line also has to go through that point. So then I'm going to plug in that for x and that for y. So 1 over 2a times a, which is x, plus 2 equals the y value, 4 minus a squared. And now that you're here, look, you just have one equation that involves one variable, so you can just solve for the variable, and that'll get it for us. So these a's are canceling. So we have 1/2 plus 2, which is 5/2, equals 4 minus a squared. So I'm going to add the a squared over, subtract the 5/2 over, combine those, 8 minus 5, 3/2. So you get a squared equals 3/2, and square root both sides, plus or minus root 3 over 2. That is another way to do that problem. I had to think about it for a little bit. I had to pause for a bit and think about it. But that is how you do that problem. All right, let's do a new one. Hopefully I can do this one first try. 2 posts, only 12 feet high, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be stayed by 2 wires attached to a single stake running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So they don't say they drew a picture for us in the book. So let's draw a picture ourselves. We have 12 posts, one 12 feet high, the other 28 feet high. They are to be stayed by attaching 2 wires attached to a single stake running from ground level to the top of each post. So I guess we're just putting somewhere in the middle, and we're going to run this wire here. So we know that's 12, we know that's 28, and we know this is 30. So where should the stake be placed to use the least amount of wire? Oh, that's a good question. So, yeah, I mean, this seems fair. So we want to minimize the length of the wire. So we got to write an equation for the length of the wire. So let's do that. So we needed some x, right? Let's do this as our x, because that'll tell us that this is x minus 30, and that'll allow us to just use Pythagorean theorem and write equations for this. So this is the square root of 12 plus x squared. This is the square root, well, not 12 plus x squared. We're going to have big numbers, 144 plus x squared. This is the square root of x minus 30 squared plus 28 squared. Wow, okay. I mean, that gets us our equation. So that means the length of the entire wire is the square root of 144 plus x squared plus the square root of x squared minus 60x plus 900 plus 28 squared. Let's see. 28 squared is 30 minus 2 squared. So that's 900. Too bad those don't cancel out. Minus 120 plus 4. Do they cancel out? No, because they're both from squared. So 900 minus 116. So that's the equation. We're going to take the derivative of that and set it equal to 0. That's a lot. That's a lot, especially if I can't combine these somehow first. Which I don't think I can. So we're going to take the derivative. 1 over 2 root x squared plus 144 times 2x plus 1 over 2 root, I guess I need to combine these. What's 1800 minus 116? $1,684. X squared minus 60x plus 1684. Oh my gosh, these are bad numbers. I don't know if that means I'm doing something wrong. It doesn't, and like in real life, you just get bad numbers sometimes. But you wonder if they make you do it in problems. So at least these 2's are canceling. So I don't have to worry about them. But if I'm going to set this equal to 0, I have 2 different fractions. I'm going to have to combine the top and get some crazy stuff, honestly. So I'm going to have x times the square root of x squared minus 60x plus 1684. Plus the square root of x squared plus 144 times x squared minus 30x equals 0? No way. So now I'm going to move this to this side and square both sides. So I'm going to have x squared minus 60x plus 1684 equals well, I guess at least they are multiplied by each other. So x squared plus 144 times x squared minus 30x squared. That's going to give me x cubes, though. Oh my gosh, I thought I was going to like this question, but this got big. Well, you know what? Look at this. This is x times x minus 30 squared squared. So I can divide both sides by this x squared. So then I'm just going to have to FOIL. Well, I'm still going to have x minus 30. But this is x squared plus 144 times x minus 30 squared equals all of this x squared stuff. So, so this is x squared minus 60x plus 900. And this is x squared plus 144. Is this really what I have to do? I mean, none of this is difficult. It's just tedious with all these big numbers. It's a little suspicious that they would make you do all of this crazy stuff. But it's also like an application problem, so I guess it sort of makes sense. I'm trying to do this no calculator, so I guess I'll continue. 144 times 6, that's not the easiest thing to do in your head. So 24, 6, 2, 8, 864. Minus 864x. 144. Oh, plus another 0. And then 144 times 900. 129600. Oh my gosh, are you kidding? So that alone is x to the fourth. Let's see the x squareds plus 1044 x squared. I didn't even hit up an x cubed. I didn't even get an x cubed because I made freaking mistakes. I made a lot of mistakes. Wait, what? I should have 6. 1, 2, 3, 4, 5, 6. So this should be an x cubed. That's the only x cubed there should be. Okay. So I'm not sure if that was even right. Oh, it was. So minus 60x cubed. I got that. And then the x squareds. So that was 1044x squared. We got those. And then the x's. There's only one x. Negative 8640x. And then the ridiculous number. Equals this. So I have x to the fourth. Yeah, that was an equals there. X to the fourth minus 60x cubed plus 1043 x squared. Now I'm adding the 60x to the other side. So that's minus 8580 x and then 129600 minus 1684 for the constant. One two seven nine one six. There's no way that I did that right. How do I keep making these ridiculous mistakes? Unless it's just a calculator problem. But I'd be surprised if they wanted to make this a calculator problem. X to the fourth. Let's just see what this graph looks like then. So I've dropped the idea that I'm not using a calculator. That can't be right. Oh, I never took the derivative, did I? Oh, no, I definitely did. So I was trying to say that that was the same as x over the square root of x squared plus 144 plus the square root of x squared minus 60x plus 900 plus 900 minus 116. Well, and that never equals 0. Hang on. Oh, because that's the wrong part of this equation. That's supposed to be x squared minus 30x divided by the square root of x squared minus 60x plus 1684. Whoa. So did I get this right? Did I then just have to go to the calculator and say, there you go? So I added a bunch of new solutions by doing it as x to the fourth. I guess I managed to also eliminate the 0 solution. But is that it? 29 feet? I'm supposed to put it 29 feet? Close to it? No way. I didn't mess up the equations, did I? No. Well, that must be right then. Do you just have to use a calculator? Is that how they wanted us to do it? Let's look at the textbook. There's our root 3 halves. We found this, 9 by 6. Wow, no. Yeah, 1684, I got that. And then you set it equal to 0. Wow, did they get down to what I got to? They got their x to the fourths to cancel. Oh my gosh, wait, what? So it really looks like they basically did the same thing I did. Where did x squared minus 30x come from? Did I not take the derivative there? I didn't take the derivative here. Oh my gosh. Yeah, that's the math we got, but I totally messed up. This is why I need more people here to check and correct my mistakes. I mean, look at this. I was like, I'm going to take the derivative of the inside, and I said the derivative of the inside was 2x squared minus 60x. But that's not true at all. The derivative of the inside is 2x minus 60. So that changes like all of this stuff. It's not going to be super easy. But it's definitely going to make it easier. That's just 2x minus 60. Oh my gosh. So I'll still cancel the 2's and call that a 30. So then I have x root x squared minus 60x plus 1684 plus x minus 30 times 2 root x squared plus 144 equals 0. So now I'm going to move this to this side. That still doesn't help a lot. Also, no, the 2 is gone. Come on, come on, come on. The 2 is gone. And I guess I'm moving this to the other side, so I'm going to put the negative in there, make that 30 minus x times root x squared plus 144. So now I need to square both sides. So I'll distribute it in here. I do get x to the fourth, though. I guess, is that what's canceling out? I get x to the fourth. And I still have to square this. And I'm still going to have to distribute that. I have x to the fourth minus 60x cubed plus 1684 x squared equals, and then here I've got to go 900 minus 60x plus x squared times x squared plus 144. So the x cubes are canceling here, so it makes things more doable. So let's go ahead and continue with this. 900x squared. 9 times 144. I already did that too, didn't I? 36, 39, 1296. And that's plus 1296. And then minus 60x cubed. Minus, and this was the 144 times 6, which I already did, but I don't remember. 864 minus 864x, and then plus x to the fourth plus 144x squared. So the x to the fourth on both sides is canceling out. The x cubed on both sides is canceling out. And let's try to move everything to the right. So I have 900x squared, 144x squared, which is 1044x squared. Oh my gosh. And the x's is just the minus 1864. So I have 1044x squared. Oh, no, then it's 1684 minus 1044 is 046, 640. So this is negative 640x squared when you move it to the other side. And the other ones are just gone. So then it's just combining like terms over here. I already combined the x squared, so it's not even combining like terms. It's just what we have. Negative 864x plus 1296. That's awful. Equals 0. I mean, I can divide by 2 as much as I can. I'll divide by a negative 2 first. 696 divided by 2 is 48. So that's 648, but it's plus now. I can divide by 2 again. 160x squared minus 216x plus 324. Can divide by 2 again. 80x squared minus 108x plus 162. Okay. So I could have divided by much bigger numbers, but whoa. 108. 54x 81. That's the end. And they want me to solve that equation? They want me to solve that equation for x? That's a little ridiculous. I can go back to the Wong method. 140, 220, 4, 10, 5, 8, and 181, 327, and 9, 9. And they have to add to get 54. So you do it across. You go like 1 times 81, 40 times 1, no. 1 times 27, 40 times 3, no. 1 times 9, 40 times 9, no. 2 times 81, 20 times 1, no. 2 times 27, 20 times 3, no. 2 times 9, 20 times 9, no. 4 times 81, no. 4 times 27, no. 4 times 9, 36. 10 times 9, 90, no. 5 times 81, no. 5 times 27, no. 5 times 9, no. So then you flip them. That's still not going to factor. I still mess something up. How am I just not being careful with this algebra? That's to be all that it is. That doesn't even have any x-intercepts. Are you kidding? Because that should be a plus. Actually, yeah, it doesn't change anything. Man. So if I go right from the jump, did I mess up at the end? I mean, I guess I did mess up from that. So what is 640 divided by 40? So I canceled out 16. What is 864 divided by 16? Is 54. What is 1296 divided by 16? Is 81. Okay. My gosh, I really just messed up these signs. This is minus 81. This is minus 81. So you're looking for a difference of 24. Man, the algebra is wrecking me lately. The algebra is wrecking me lately. So I'm trying to subtract to get 54 in the middle. So let's see. Let me do our other ways. So I'm trying to have them subtract to be 54. So I still don't like the 1 and the 40. I still don't like a lot of these. So 2 times 27 is your 54, but then you're going to be subtracting 60, so that's not going to go. But that is small, which is my problem for a lot of these is they're not small. And 4 times 1, 10 times 81. See, 10 times 81 and 10 times 27, there's just no way that's going to cut it. With the 4 times 3, so then 10 times 9, 4 times 9. Oh, that's it. That's it. This is 4x plus 9 and 10x minus 9. Did you get positive 90x and then minus 36x? Oh my gosh. So I get x equals 9 over 10. What? And x equals negative 9 over 4. I can't have x be 9 over 10. It should be bigger than 15. Are you kidding me? These are not good videos. But if you're willing to sit through and watch me struggle, they can be good learning opportunities. So I'm looking at right after by letting that equal 0. And then I want to see how they solved it. So they got x squared minus 60x plus that. And that's, right, 30 minus x. They did the same thing I did. Times that. And they squared both sides. So that's why it was squared. So I did that. On the left, they got x to the fourth minus 60x cubed plus 1684x squared. That's what I got. Over here, they got... Well, let's just see what they got it down to here. Oh my god, did I drop zeros? I dropped zeros. Oh. That has a zero. That has a zero. Oh my gosh. I was doing the multiplication and then I got the answer and I just put it. I forgot I wasn't doing 144 times 9. I was doing 144 times 900. So there's a 0 on that and there's 2 zeros on that. So now I can divide stuff, but also just take out zeros. I don't know if I can... feel like I need to restart the division stuff. So I have negative 64. Let's just go ahead and change the signs for real this time. 64x squared plus 864x minus 1296 still has that 0 there. Now I'll do the divide by a bunch of stuff game. So 32x squared plus 432x minus 648 with a 0. And do it again. 16x squared plus 216x minus 3284 with a 0. Now I can do it again. 8x squared plus 108x minus 162 with the 0. And then 4x squared plus 54x minus 8100. But now I can do it again. How did that get so much lower so much quicker? I guess because I dropped the 0. It was 640. So now 2x squared plus 27x, that'll be the end of it, minus 405. So now I would do the Richmond method, and I would look at 810. What multiplies to be negative 810 and adds to 27. So what about like 9 and 90? Well, no, definitely not. Like 18. As if 9 and 90 work. 9 and 90. I could do 18 and 45. And that'll work. Because this is 9 times 10 times 2, so I'm bringing the... Or 9 times 5 times 2, so I'm bringing the 2 over there. And that'll work. So that's going to make it x plus 45, x minus 18, divide by 2, divide by 2. So I get 2x plus 45 and x minus 9. So I get 9 and negative 22.5. I thought they had those switched. No, 9 and negative 22.5. And yeah, we knew that negative 22.5 was not in the domain. So it has to be 9. Should be 9 feet from the 12-foot pole. Man, it doesn't even feel successful. I messed it up so many times. And I went so far into the next problem. But these are tough. I mean, they're all thinkers. And then you see all the algebra. If I could use a calculator, this would be way easier. Maybe I should do it like that, because that's the real emphasis. Like, is just setting it up, not all this algebra. You don't need to be able to solve these massive quadratic equations to be decent at calculus. Just makes it more fun so you don't have to sit there and grind like this for every single thing. All right, here's the last one. So 4 feet of wires to be used to form a square in a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the total maximum area? Okay, so the wire is 4 feet long. And we're going to make a square and a circle. How much of the wire should be used for the square? How much should be used for the circle to enclose the maximum area? So we need, oh my gosh. Well, so our area is we have the area of the circle and we have the area of the square. So we have r squared and we have x squared. Oh man. But then the wire, we have circumferences and stuff. So we know that the circumference of the circle, 2 pi r, plus the circumference of the square, x, has to equal 4, because that's the length of the wire. So now I'm gonna solve that for x. Or for r, but I'll solve it for x. So now my iPad did not just die. My entire iPad just crashed. Holy moly. iPad can't handle the math. Oh my gosh. We're back though. We're back. So yeah, we're going to do what I said. So I'm going to solve for x. So x equals 4 minus 2 pi r divided by 4, or 2 minus pi r divided by 2. Let me make sure I'm going slow so I don't mess this up and have to do it a million freaking times like all these other ones. So I'm subtracting the 2 pi r and I'm dividing by 4. So all that's being divided by 2. Okay. So now I'm going to write that in the area equation. So now my area equation is pi r squared plus 2 minus pi r squared over 2. Also squared. So that's it. Now we want to take the derivative and set it equal to 0. Okay. So let's do that. So we have 2 pi r plus, let's see, the power rule is going to cancel with that on the bottom. So it's 2 minus pi r over 2 times the derivative of the inside times negative pi. And we're trying to set that equal to 0. I said pi, I wrote infinity. So I can multiply by 2, 4 pi r plus, except for minus, pi, 2 minus pi r. And all of that equals 0. So I'm going to solve for r. It's going to involve a lot of pi's, but that should be okay. So I'm going to distribute 4 pi r minus 2 pi plus pi squared r equals 0. And then I've just got to factor out the r. So I have r 4 pi plus pi squared. And then add this over equals 2 pi. So then I'm going to divide by 4 pi plus pi squared. And you're right, the pi's are going to cancel. So that's 2 over 4 plus pi is the radius of the circle. Is the radius of the circle. I suppose I'm going to want decimals here. So let's do that. 2 divided by 4 plus pi. 0.28 as the radius of the circle. Pretty much right on 0.28. And then, so then what's the circumference? What's the wire? So that times 2 times pi. So you're using 1.76 for the circle. And so 1 minus that. Not 1 minus that, 4 minus that. So that plus 3 is that you're using 2.24 inches for the square. But that's not right. That's not right. I know that that's not right. Gosh, I am sick and tired of getting these problems wrong. The length of the wire is 4. So we know the circumference of the circle is 2 pi r. And the radius, or the circumference of the circle is 2 pi r. The perimeter of the square is 4x. If x is the bit of each bit of wire. And r x is the side length of the square, r is the radius of the circle. So I solved it for x. I did 4 minus 2 pi r divided by 4. So I made that 2 minus pi r divided by 2. And so I put that in for x. I included that. I made this 4. So I made that squared. I squared that 2. Then I took the derivative, so it was 2 pi r. I did power rule, so the 2 came down, canceled out one of those 2's. The new power was 1, so 2 minus pi r times the derivative of the inside, times negative pi. And then I multiplied everything by 2. I set it equal to 0, so I could multiply everything by 2. So it was 2 pi r. The 2's canceled, so it was just negative pi, 2 minus pi r. I distributed the negative pi. Negative 2 pi plus pi squared r. 4 pi r minus all of that. I tried to solve for the r. Well, that's what I wanted to do, is I wanted to solve for r. So I factored stuff out, and I definitely got that. I'm like pretty confident that I did stuff right here. But I'm also pretty confident of what the answer should be. The length of the total wire is 4 feet. Circumference 2 pi r. Perimeter of the square 4 times x. The area is pi r squared and x squared. I definitely had all that stuff distributed. I multiplied everything by 2 properly. And the derivative of the inside is negative pi. It's so frustrating. Let me pause. I'm going to go look at the answer real quick. All right. So we did all of this properly. But here's what's wrong. Is that we have to look at it now. Is I guess maybe we should have done this every other time and we didn't do this. But it does matter for this. So here's what we found. We found that is like a critical value. 2 over 4 plus pi as the radius. Which would get us this much wire for the circle and this much wire for the square. So then what are the areas? Well, if this was the radius, that means the area of that circle is pi times 0.28 squared. So the area of the circle is 0.246, while the area of the square is, well, I found that this is the perimeter of the square, the 2.24. So if I did 2.24 divided by 4, that's the side length of the square. And if I square that, I only get an area of 0.313. And if I add those together, I only get an area of 0.56. And so the deal is you've got to check like the endpoints here. You've got to check. So that's the area with the critical thing we found, but that's not necessarily the maximum. That actually might be a minimum, and I think here that is a minimum. Because if we check just the endpoints, we check like if x equals 0, if 0 of the wire is used. Well, yeah, we got if 0 of the wire is used for the square, and if 0 of the wire is used for the circle. So if all of the wire is used for the square, that means that it's 1 by 1 by 1, and that would be an area of 1. And see how already that's even better to just do the square. And if you just made the circle, well, you'd have to do some math for that, because then you'd go 4, that would be the whole circumference, equals 2 pi r. So that means that the r would be 2 over pi. And then when you found the area with that, 2 over pi squared times pi, I guess I could have done that better. You get an area of 1.27. So look at that. We do need to check and make sure we're doing right. Normally it works out that when we're set to do this, whatever we get does that, like finds it properly. But no, we found the minimum. We didn't find the maximum. The maximum is actually this. And there we go. That's the problem. That's it. So the answer is to use all of the circle. And that makes sense because we should have a decent intuition in our heads about circles are a better way to maximize area. Because you don't have the corners. You think the corners kind of jet up there, give you extra perimeter that you don't get all that area for. And that's why balloons blow up in circles. That's why bubbles are spheres. Because circles are the most efficient way to pack area. There we go. This was a long video. I apologize for how many mistakes that I've made in it too. But, it is what it is. You just got to slow down. You just got to be careful. And you got to trudge through the math and do your best to not make mistakes. These are fun problems. It's just easy to make mistakes on them.